Good afternoon, everyone. Thank you for joining our webinar today. Today with my colleague Denise and Milat, we are going to present you new features, new options that you can find in our new release 10.8. We are very proud of this release. This release is available since late December, just before Christmas. For the one who subscribed to our newsletter, you probably have received the information, and maybe you have already installed this version on your PC or server. And of course, for the one who haven't done that yet, I invite you to take a look at our website where this version is available for download. The webinar will be recorded, so the video will be available within a few days on our YouTube channel. During the presentation, your microphone will remain muted, but there is a question box where you can type your questions. And at the end of this presentation, we'll take a look. And if there are some questions that can be interesting for the audience, we will answer on the fly. Otherwise, we will get back to your question per email. So having said that, let's start. And let's see what's new in this 10.8 version. So we are going to give you an update on the update and development on the modeling features. Also, what's new in terms of material model analysis and results, and also an overview of our new tutorials and a documentation page. Let's start with one feature that has been on our wish list for a long time. This is user coordinate system. So in Diana 10.8, it's now possible to define a user defined coordinate system. It can be of three types. It can be Cartesian, cylindrical, and spherical. And you can define it under the reference system section. Then you get add coordinate table where you can specify the type of coordinate system that you want to define. This user-defined coordinate system is applicable to the nodal results output. So it means that you can select a specific user coordinate system for the output of nodal results, such as displacement, velocity, acceleration, and forces. For instance, in this slide, we have an example where we have the displacement in the global x direction on the right and in the radial direction on the left. So this is something new, and it has been requested by many of you guys, so I think it will please quite a large group of users. Another another new feature in 10.8 is the possibility to apply distributed forces on faces and edges, considering the local element directions at the direction of the load. Previously, up to Diana 10.7, it was only possible to consider normal and global direction as the direction of the load. Now you can choose between the element X, element Y, and element Z direction for the load direction. The representation of this distributed load applied in the element local direction on surfaces at the geometry level is by default made by means of a small square symbol in the surface and lines representing the magnitude of the load. The reason for this is at the geometry level, the element type is not yet known, so it's not possible to completely define the element local axis. Once you mesh, this information is known, and basically the element types and the element local direction are known, so we can display the direction of the distributed load as well as the magnitude. So this is the representation that you will get at the geometry level, and this is what you will see at the mesh level. So you will be able to visualize a circumferential or tangential distributed load applied in the surface of a cylindrical shape, for instance. Now it's also possible in 10.8 to derive local element axis from cylindrical, conical, spherical, and torus surfaces. So next to the direct input option, you can choose one of these system. It means that when you use one of these derived system, you can also present some of the output in this local axis, such as the stresses and the strain. So in the output section of your analysis, if now you go for strain local or strain or stress local, it will present the stress and strain in the local axis, whether it's derived from a cylindrical surface, conical, spherical, or torus. This feature opens new modeling possibilities. It allows the definition of material orthotropy for solid shapes in other coordinate systems. So you can do that in cylindrical, conical, spherical, and torus. On this screen, we have an example of a cylindrical system. It also allows the definition of distributed load applied to element local axis following other coordinate system. So what I said in the previous slide about the element direction can apply there, but not only in Cartesian system, it can apply to cylindrical, conical, spherical, and torus surfaces. So the possibility to define your loads are now quite extended. In previous Diana version, it was only possible to define the local reference reinforcement x-axis through the vector component in the global coordinate system. This has been extended in 10.8, and now you can define the local reinforcement x-axis using the derived from an in-plane circle method. This possibility is quite useful and practical, especially if your reinforcement have a circular disposition. It can typically occur in the construction of wind turbine foundations. So this is a nice feature, and you see that when you present the local element axis, this are following basically this in-plane circle definition, where the tangential direction in the plane of the grid, the local z-axis is the normal, and x will be the radial. So similarly to the previous slide for grid reinforcement, it's also possible to define the radial local axis for shell element using the same principle. So you can also derive it from an in-plane circle method. And basically, your x, y, z will be following the radial, tangential, and axial direction of this in-plane circle. This method is also available for 3D plane stress element and composed surface element. So these are the main elements where this method can be applied. The hydrostatic force load applied to sheet pile walls has been extended again in 10.8. Again, in the sense that in previous Diana version, 10.7, the hydrostatic force load applied to sheet pile walls was automatically generated in stage construction analysis. In 10.8, this is also the case for structural nonlinear analysis. In the case of structural analysis, the automatic generation of the hydrostatic load is applicable to the sheet pile walls and not to the regular element edges. For the geomechanical stage construction analysis, this load automation is applicable to the sheet pile walls and the regular element edges or faces. So it's now time for me to hand over the presentation to my colleague, Milat, who is going to talk about generalized plane strain, and cooling pipe in 2D. Milat, the floor is yours.
Can you see my screen?
Yeah.
Perfect. Thank you, Jean-Claude, and good afternoon, ladies and gentlemen. I'll be talking about two modeling possibilities that we have now in 10.8. First one is a new modeling dimension that is available in Diana called generalized plane strain with out-of-plane rotations. You can refer to the manual for more details on the differences between this new type of generalized plane strain and the existing one. This new option is most useful when your 3D structure cannot be represented by a conventional plane strain model, only because it is not constrained in the out-of-plane direction. So if the model geometry, loading, and etc. satisfy plane strain requirements, but it is allowed to deform in the out-of-plane direction, then generalized plane strain, this new version, comes into play, where basically it is a two-dimensional analysis, so you will have a lot of computational saving, but in addition to in-plane deformations, we now also have out-of-plane displacements with this new type. And because of compatibility requirements, these out-of-plane deformations must remain planar, and this is guaranteed by an automatic internal tying. And you can define a model to be this type of generalized plane strain when you make a new project, as you can see on the right-hand side. The other new modeling option is related to heat transfer problems. In transient heat analysis of concrete with heat of hydration, cooling pipes, and stuff like that, it can be computationally very expensive when a 3D structure, which is relatively long in one direction, is modeled. For this reason, we are now providing 2D version of cooling pipes as well, which are developed and rigorously tested, which can again save a considerable amount of analysis time. There are two main assumptions that should be considered. One is that the 2D structure, the section that now you can use with the cooling pipe, represents the mid-length of the corresponding 3D structure. And the second assumption is that the temperature of the continuum, concrete, and the coolant, most of the times water, are constant in the out-of-plane direction. For this 2D cooling pipe, you can use both conventional plane strains for the continuum and also the new type of generalized plane strain, depending on the geometry and boundary conditions of your 3D structure. There's also a new tutorial explaining modeling procedure in much more detail. For modeling, the very first information that should be provided is the out-of-plane thickness of the 3D structure. This is given when making a new project in model thickness, as red circled here. And to define the cooling pipes, we first need to make a cooling pipe set under geometry. And then we can add the cooling pipe points. And finally, we can assign material geometry and flow direction. These again are shown in more detail and discussed in more detail in the tutorial. This new way of defining cooling pipes can also be used in 3D models. So that would be it for me. So I'm giving to Denise.
Thank you, Milad. Good afternoon, everyone. So I continue with new models or new enhancements related to materials. And I start with this new option for Coulomb Friction model for structural interfaces. So it's now possible to define the nonlinear elasticity by means of user-defined diagrams that define the relation between normal and or tangential relative displacement versus normal and or shear traction. And to do so, so this is the dialogue of the Coulomb friction material model for structural interfaces. So you can select here the aspect to include, that is the combination with nonlinear diagram. And then here you have the tables to input these user-defined diagrams. The next one is the possibility from the NIE to define the material model for the rotational springs and dashpots with the rotation stiffness diagram behavior. So you see here that for the spring behavior, you can select now rotation versus stiffness diagram, and then you have the option to input this graph, this table of rotation versus stiffness. This was something that was possible before, but only through syntax, and now it's available in the GUI. The next one relates to user-supplied material models. So now it's possible to define user-supplied material models for the material classes of steel. You have here the example, class steel. At the drop-down list, you will find the user-supplied material model. This is also the case for interface elements. It's also there, and it's new. And also for the bond slip reinforcement material model, it is now possible to define the user-supplied material model for the bond slip interface failure of the bond slip reinforcement bars. So this is new because before you could only use user-supplied material model under the material class of concrete and masonry, and also soil and rock. So extended to these cases now. Also in Indiana 10.8, we have a couple of enhancements related with the input of fiber reinforced concrete tensile curve. This is the first one that we present. So now you can input this curve by using the fiber reinforced concrete curve from the model code 2010. So it's much easier to input to define this tensile curve, because you select the material properties based on the model code, and Diana will derive this fiber reinforced concrete stress versus crack mouth opening displacement relationship from the equations of the model code. The other enhancement related with fiber reinforced concrete is that also in the total strain based crack model, we can now define this curve by means of force versus crack mouth opening displacement. So this option here is new now, and this allows for a more direct input of the experimental data that is usually obtained from the 3-point bending test performed in the notched specimens. The next one is that for geotextile simple stress model, you can now consider orthotropic elastic behavior. Before it was only isotropic. And this can be applicable to modeling textile orthotropic behavior in 3D membranes. So here you find the option of orthotropic in the elasticity type of the simple stress model. The next one is that for the steel simple stress model, it has been made available. So it's a new material model for the steel material class. So this simple stress model for steel is based on elasticity and allows for the consideration of no compression or no tension. And now I give again the floor to Jean-Claude.
Thank you, Denise. Let me get back to, so you can see my screen now. So let me give you a quick update on the enhancement of the geomechanical stage construction analysis. In Diana 10.8, it's now possible to add geometrical nonlinear settings to the geomechanical stage construction analysis. up to 10.7, it was only possible for the phased analysis. So this has been extended to the geomechanical nonlinear analysis. You can select the type of geometrical nonlinearity formulation from two options, total Lagrange formulation or updated Lagrange formulation. This option can be found under the nonlinear effect of your analysis. And through the property window, basically, you can select one of the two methods and activate or deactivate this option. Another enhancement is the possibility for switching in a given stage the drain condition of a material. This was also possible in 10.7, but only for phased. So now this is also possible for the geomechanical stage construction. So if a material is defined as undrained, it can change at a given phase to drain behavior by selecting the option force drain behavior of undrained material in the property of the corresponding stage. Please note that the inverse is not possible. So you cannot ask a drained material cannot be switched to the undrained condition. So it's only one way. Let's continue with some update on the results and output feature. In 10.8, we have a new operation for stress output for calculating distributed force and distributed moments in shell elements according to the wood and armor method from the Eurocode 2. So with this method, you can calculate two types of design distributed moments. One for the lower part, positive, causing mainly tension in the bottom part, and the upper one, which is negative, causing tension in the upper part. By this results, it's a combination of the result in the local direction, the bending component, with the twisting component. The same is available for the distributed force. So basically, you have an option which is this mom 1 mole for the moment, and another one which is 4 for the forces. So this is a new output, and you can take benefit of it. This new result operation for wood armor method is also available for composed surface element in combination to the shell element. So you can, in a similar manner, that what is computed for shell element, you can also ask for this result for composed surface element. So it will give you some distributed moment and distributed forces based on this combination. So I'm going to give you back the floor, Denise, so that you can continue and finish this presentation.
Thank you, Jean-Claude. I will continue with a new item in results. So for the principal tensor field visualization, in previous IANA versions, we had the so-called in-plane principal stresses that were represented by means of two-dimensional rosettes and normal stress component displayed as counterplots. So these in-plane principal stresses are now replaced in IANA 10.8 by a conventional representation form. So now what we have is the principal components of any tensor field represented by means of two-headed arrows at the center of the element and located at the superficies of the model. So now I will conclude this presentation talking about the tutorials and documentation. We have 4 new tutorials. The first one is about user-supplied material model. This is a very simple tutorial that demonstrates how to consider a user-supplied material model in IANA. So it presents a very simple function that is compiled in Fortran and then we use it as the user-supplied material model in a Diana very simple model, and we can see the differences of changing the parameters in the results. The second new tutorial, it's about identify and unite disconnected nodes in closed interfaces in Diana. So there's sometimes after the creation of interfaces, some nodes get disconnected that are not wanted by the user. And this tutorial aims to help users with a workflow to look for these disconnected nodes and merge them back or unite them back. The third one is about restart of a nonlinear analysis. Again, this the goal is that this is a simple tutorial, straight to the point, to demonstrate how to restart nonlinear analysis. This is a transient nonlinear analysis that stopped for some unwanted reason. In this case of the tutorial is divergency, but in real life can be hardware problems, that data storage limits, etc. Then as Milad already mentioned, we have a new tutorial that demonstrates how to use our new feature of cooling pipes in 2D models. So what we did was a 2D version of an existing model that we have in our tutorial, heat flow analysis of cooling pipes in young hardening concrete. So here in this existing tutorial, we make a complete 3D model of a tunnel, and we took one slice of this 3D model, and we did it or redo it with a 2D version, and got related results. About the user coordinate system, we took one existing tutorial, is the wind turbine foundation, and because it's circular, so it was good to demonstrate how we could use a cylindrical user coordinate system to output. For example, here you can see displacements in the radial direction. Also for the new input of the fiber reinforced concrete tensile curve based on the model code 2010 in the total strain based crack model, what we did was also using existing tutorial, that is the bending test on a fiber reinforced concrete notched beam, and made an extra slide exemplifying how you could alternatively input your tensile curve by means of the model code 2010. So about general documentation of Diana, we during the past months we were already using this new portal, but now it's the opportunity to present it. It's the Diana fixed issues page. So here we list the most relevant bugs that are fixed in each update version of a release. You can access this page. You need a login credentials, so you need to contact the Diana support. I give again the floor to Jean-Claude so he can conclude.
Thank you, Denise. So thank you all for attending this webinar. I hope you get a better feeling about the new options and features in 10.8. We strongly invite you to use these features, and we would be more than happy to hear your comments, feedback, suggestion about these features. So please do not hesitate to download Diana 10.8. As I mentioned in introduction, this is available on our website. For any user with a valid subscription, you can download it, use it without limitation. So please challenge it. As you could see, there's also a lot of new tutorials to also explain and facilitate the usage of these features. These tutorials are also available on the website. So please take a look at them. And yeah, as I said, I mean, we would be more than happy to hear your feedback because the general idea is not only to add up features, it's also to make features that you can take benefit of. So having said that, I don't think there are any questions. So I'd like to thank Milat and Denis for helping me for this presentation. And I'd like to thank you all for attending this webinar. I strongly invite you to keep an eye on our website. Soon we will be our event calendar updated for 2024. So you will see the event and course and the seminars published on this website. So also do not hesitate to register to our newsletter so you can be informed about the latest update about our company and software development. So thank you all for attending this webinar, and I wish you a pleasant end of the day or pleasant end of the morning, depending where you are located. And I'm sure we will be in touch in the near future in one of our online activities. Thank you all. Bye.